All right, good morning, everybody. So today is Linear Algebra Day at MIA. I'm Jon Bloom, and Hoon Cho will also share this primer with me. And then later we'll hear from Gil Strang in the main talk on the key ideas of linear algebra. So as a primer, most of what I'm going to discuss is not new. I'll indicate at the end of my part maybe what is, and I'm sure Hoon will share some new things as well on his end. I'm going to focus on the distributed aspect of linear algebra, and Hoon will focus on the privacy-preserving aspect. And I hope you'll be convinced that these are actually quite related, which is why our primer is joined. So to start things off, the key question here is how do we compute on big data divided among a bunch of parties? And you know, a reasonable question is, well, why? Why would you want to divide it among parties in the first place? So just conceptually, let's imagine that I have some vector x, okay? And I want to compute the length of x. But x has maybe 10,000 coordinates. So it's a high-dimensional vector. And in fact, I'm just going to give you this vector. I'll have 10,000 note cards, each with one coordinate on it. And I'll give you these 10,000 note cards, and I'll just say you can't get breakfast until you tell me the length of the vector. Right? So what might you do? Well, probably you aren't going to have just one person sitting there going through this stack of note cards, squaring each number, adding them up, and then taking the square root. What you'll do, most likely, is you'll each start churning through note cards, squaring and adding, and you'll each get some small intermediate sum, and then maybe come to the whiteboard, write it down, and then someone else will just start adding these intermediate sums together, and that will more quickly, get you to the final result. So that's a pretty simple example, but it already illustrates maybe the first answer to why you might want to divide your data up, because you might want the data to be partitioned for parallel processing. So that's to speed things up. And in that example, the partitions of data or the parties controlling them are you're all a bunch of processors, right? And we just want to allow you all to work in parallel. A second reason is that the data may already exist across space, and that it's costly to transmit it or to copy it. So if Broad has some data and the Sanger Institute has other data, and it's petabytes of data, we may not want to have to move all that data to the same place because it's very expensive to keep many copies, or simply in these distributed systems, the network can be very slow as a bottleneck. So just communication is costly. It could also be that the data exists across time, meaning you've done the computation on the data you have, but then next year a whole new batch comes in. And so what you want to be able to do is some sort of incremental update where you don't have to redo all the computation on the first part just to add in the new data. And then the final reason I could think of relating to the more privacy-preserving is that it could be that the data must remain private. And nevertheless, multiple parties may want to run a joint model on all the data and share the results without sharing the underlying data. And this privacy could be, again, because maybe there are HIPAA regulations preserving patient privacy. Okay. And what this suggests in all these sort of situations is that the following strategy would be pretty useful. A kind of aggregation strategy that we just described as a room for computing the length of a vector that is a two-stage algorithm. So the first step is that each party compresses their big data, and that can be done in parallel, which is nice. So they're compressing their big data. And then the second step is all parties combine their small intermediate results and then basically finish their computation, so to arrive at a final answer. In the vector length case, combining is just adding, and then to arrive at the final answer, we have to take a square root. Okay? Now, I want to note here that already, because we're only sharing sort of small data, because communication is expensive, for example, this already confers some amount of privacy. But we're not talking that much to each other, so how much can we really give away? But if we really want theoretical guarantees, the smallness also makes what's shared amenable to cryptography, where you encrypt the things you're sharing, finish the computation in some encrypted form, and then just decrypt and share the result. And Hoon will tell us how to actually do that in practice. All right, but it's key that the data is small at the point that you need the cryptography, because cryptography tends to have a huge overhead. It's very slow to do the encrypted computation relative to the plain text. So you couldn't just encrypt the huge data at the beginning and do something altogether encrypted. It would just take forever. So first, make it small, and then use cryptography on small things to get at the final result. Great. Okay, so the rest of this talk is going to be motivated by the use case of running a big multi-party GWAS, genetic association study. And to get there, I'm going to do it in 3 stages. So stage 1, talk about dot products in the multi-party setting. In stage 2, linear regression with a focus on simple linear regression. And then stage 3, we'll talk about how to do GWAS efficiently using these ideas. And most of these ideas are old. The very last idea maybe is novel. I should say all of this is available at the URL. It's a repo called Dash on my Git, and came out of discussions with Cotton and Alex Blumendahl and Ben Neal and so on. It's how Hale runs GWAS, for example, in the single party setting, and maybe eventually in the multi-party setting. So, moving on to dot products. So we already sort of did this because the length of a vector is just the dot product of the vector with itself, square root. But suppose we had 2 vectors, x and y, and suppose that one party owned half the coordinates, so this top part I'll call xa. A is for Alice, the usual cryptography party, and then xb is Bob. So Alice also owns the top half of y, and Bob owns the bottom half of y. So think of this axis as we're in n dimensions, and these are sort of our sample axis. Okay? So we want to compute the dot product. Well, as we just kind of observed, for x dot x, for x dot y, it's the same deal. You can think about this as xa dot ya plus xb dot yb. So each party computes the dot product within their coordinates, and then you add them together. So as an exercise, you can confirm that this generalizes to the matrix case. If x was a matrix, not just a vector, it had a number of columns, and maybe y as well, then the same formula works, if I can get my letters right, in that case. Except instead of dot, we're going to use transpose. But essentially, every coordinate in this result is just a dot product like this, and that's why it works. XB transpose. Okay, so these kinds of computations, you already see a strategy for how we can do it in these two stages, assuming each party owns half the rows. So now we're going to reduce linear regression to dot products, and then we'll have a strategy for linear regression. Let's do this with simple linear regression. So here are some dots. And by simple, I mean like super simple, as in y equals beta x plus epsilon, not even an intercept. All right? And what we're interested in is the line closest to the data in the sense of these squares. So here's maybe the best fit line, has to go through the origin, and we have these residuals, and the sum of the squares of those, we're trying to minimize that. So what does that look like? We want to minimize epsilon, or its length rather, or its squared length. But epsilon we can think of as y minus beta x squared. That's our goal. How do we do it? Well, if we think a bit geometrically about linear regression, then if we're working in n dimensions, where n's the number of data samples here, we have a vector y, like this vector. We have a vector x, and maybe I should get rid of the axes because we're in very high dimensions. We have a vector x, and to minimize the squared distance between y and some multiple of x, we're going to do orthogonal projection. So this vector is beta x, and this vector is the residual vector, y minus beta x. The thing we're minimizing is literally that squared length. Okay. So if you remember back to vector geometry, this gives us a formula that beta should be x dot y over x dot x. That's just in terms of dot products. That's nice. And the other thing we're going to need, right, is the estimate of the standard error, or the squared standard error, if we want to compute, say, a t-statistic and a p-value. And so the unbiased estimate is 1 over n minus 1 times the squared residual. It's the mean squared error. Okay? But because of this right triangle, we can compute this squared length as the hypotenuse squared minus this leg squared. So we can write it as y dot y minus and I'm writing it in a sort of funny way because I want to emphasize that the result only depends on, well, what? So what do we actually need here to get our result? We need to know x dot x, x dot y dot y, and the total number of samples n. Yeah, that's all we need. So if we have a strategy for how these two parties could compute these guys in a form like that, we're pretty home free. So more concretely, the strategy is that Alice computes xa dot xa, xa dot ya, ya dot ya, and also has some number of samples. And then the same thing for Bob, just with b's. And then the second step, you add them up to get x dot x, x dot y dot y, and n. And then you compute from those beta and the standard error. Okay? And again, if we were unhappy about having to share these intermediate things, one could sprinkle some cryptography, but notice that how much data is Alice and Bob actually sharing? They're only sharing 4 numbers. The amount of data they're sharing is totally independent of the sample size. So tiny data, already kind of private, but cryptography can make it provably so. I'll note that this generalizes to multilinear regression, where the relevant quantities, if you have a design matrix capital X, are x dot x, x dot y, y dot y in n. And it generalizes because of this formula. So you can do multivariate regression the same way. OK, so now we're ready for GWAS. And what's different here? So in GWAS, we have the following data. We have a huge matrix, potentially, of n samples and m variants. So this is our genetic information. And we can call a single column of this x. Okay? We have our vector y. So this is little x. The big matrix maybe is big X. The y, so this is genetics, or these are the genotypes, which would be like 0s, 1s, and 2s, encoding homozygous, reference, heterozygous, and homozygous variant. This is our phenotype vector. And then we might have some covariates. So we'll call this matrix C. And maybe this is n by 1. Here, this will be n by k. So we have k covariates that we want to include in our model to deal with confounding. These could be principal components. Hoon will tell us more about how to compute those. Or they could be things like age or sex or other confounders. And our goal in GWAS is for every variant, and there might be millions of them, we want to compute what? Well, our regression model looks like y equals beta x plus c gamma plus epsilon. Here, gamma is a k vector. It's the k effect sizes on the covariates. And the beta is just the number. So the number we want to compute the effect size, beta, and the standard error. Just like before, but we got to do this for millions of variants. And in every case, we want to control for these other confounders. Right? So this is the key piece we want to compute. All right. So the first thing to note, right, there are two remaining points then about what we need to do. The first is we want to take advantage of the fact that we only care about this coefficient per variant and save some time not having to actually bother computing the gammas. That's going to save us a factor of k, and I'm going to give us a formula that lets us do that in a second. And then there'll be one remaining issue, which is maybe the new fun part. OK, so I'm just going to tell you a formula, and then I'm going to justify it. So my claim is that, and I'll just focus on the beta. The formulas for the standard error are analogous to what I wrote over here, and they're in the note as well. The claim is that beta hat is given by the following. X dot x minus q transpose x dot q transpose x. Sorry, the numerator should have a y. Divided by x dot x minus q transpose x dotted with q transpose x, where q is the where this q is coming from the QR decomposition of the matrix of covariates C. So C has a shape like this, n by k. Q has the same shape, n by k. And the key property is that the columns are unit length and pairwise orthogonal. So this gives us an orthogonal basis for the column space of C. And R is an upper triangular matrix with positive diagonal. And given those properties, generically, the QR decomposition is unique. Okay? So here's a formula. Let's believe it for just a moment. If we believe the formula, then we can see there's something very analogous to do, which is in step 1, well, I'll just write down the key quantities we need, and they can be computed in the same two steps. What are the key quantities? Well, x dot x. So we need x dot x, x dot y, Q transpose X, Y dot Y, Q transpose Y, and N. Okay, these are the key quantities we need, and one from there, and you don't see Y transpose Y, but it does show up in the formula for the standard error, just like you see it here. So that's why we need it. Okay, so what's the point? The point is that if we believe this formula, and if we're allowed to share the Q, then each party can compute their shares of these quantities, and then what are they actually communicating? Here they're going to communicate one number. Here's one number. Here's a k-dimensional vector. One number, k-dimensional vector, one number. Very small data, independent of n. And I also want to draw a line here to say that this side is per variant. The other side is sort of once overall. It doesn't depend on the variant. So we can ignore all the cost over here because we just do it once. Here we do it 1,000,000 times. Okay? So what you see is that the local sort of computational cost is it's really going to be about taking this matrix times this vector. So each party has to take this n by k matrix and multiply it by an n vector. So locally, you have, in plain text, order nk compute per variant. It would naively be nk squared if we didn't have this formula, this trick. But then, what is the sort of shared or global computation size? Well, we have to share k numbers per variant, order k, and then there's going to be a dot product. That's just of k vectors. That's order k. This is order 1. You look at this formula, what you see is that sort of in the shared setting, it's sort of order k in both memory or communication and compute. Okay, so time is moving really fast. What I want to do is draw just a picture that hints at how you could justify this formula. Except I have to get the right sheet of paper. Maybe I'll have to move back over here. Yeah.
Okay, maybe.
Sorry, go ahead.
So in this case, just to clarify, does each party have access to all the variants or some sample, or?
No, oh, sorry. I meant to draw a line like this all the way across. So here's like CA, CB, YA, YB, XA, XB. Or it's chopped up this way. Okay, so here's the picture. And then I guess exercise is to derive that formula. So here's a vector y. Here's the vector x beta, beta x plus c gamma. And there'll be some residual epsilon. This is a right triangle. When we project, if you imagine projecting away the contribution of c, so projecting onto the orthogonal complement of c, which is this plane, then you're going to get a picture that looks like this, where this is the projected version of this quantity, but since we're projecting away the c, we just get p beta x. This here is py, and the key thing to prove is that this is still a right triangle, and that this vector epsilon is exactly the same vector epsilon we started with here, so that you get a formula of the form py equals px b plus epsilon with the same beta and the same epsilon as in the original problem. So fitting this gives you the same result, and it turns out that p is given by the identity minus QQ transpose, where Q came from that QR. If you put these things together, you can get that formula. Now, what I don't have time to explain is how to avoid sharing the Q, which violates our policy. We don't want to share any sort of n-dimensional data around. Turns out you don't need to share the Q. One thing you could do is share the R, because if C equals QR, then Q is R inverse C. And notice R is just K by K, so it's small. So that's one thing you could do. But you're still leaking some data by sharing the R. It turns out that the R that we need is actually given by the QR decomposition. Sorry. The overall R for this matrix C can be computed by each party doing their independent QR decomposition just on their part to get two matrices, in this case, RA and RB, and then doing QR decomposition on that. The proof is actually quite short, and it's not novel. It's used in the TSQR decomposition algorithm, tall, skinny QR. It's in the paper, but the point is there's a way for each party to do their own QR, share the Rs, stack the Rs, do QR on that, which is tiny data, and then you can be a little more clever and not even have to give the R back to each party. You can make the whole thing go through with complete guarantees on privacy. The only thing learned in the end is the final statistics. So to give Hoon his fair share of time, I'm going to cut it off there, and we'll take questions at the end or in the discussion.
All right, so I want to start the second part of this talk by reminding ourselves of the overarching goal, right? So we have these computational analysis tools that we want to apply to large-scale biological data sets. And oftentimes, these will be linear algebraic operations, like estimating the parameters of a linear model, like in the case of GWAS, or performing some type of matrix factorization, which is useful in a wide range of settings. And the idea is we want to apply these tools to as large a data set as one can possibly put together in order to obtain accurate statistical insights from these data sets. Now, in the genomics or the medical setting, we often find ourselves in a situation where a lot of this data is scattered across different data holders in different academic labs or hospitals, companies, biobanks. And because of the sensitive nature of biomedical information, it's often difficult to share data across these different entities. So the driving question of this part of the talk will be, how do we enable these analysis tools on distributed data sets while preserving privacy? So let me make this idea a little bit more concrete. Oh, thank you, John. So this is distributed algorithm in practice. All right, so we have different parties that are each holding on to different pieces of the data. And together, they want to compute some joint function over their combined data set. So this could be GWAS, for example. So in an ideal world, what we would do is we would find a third party, a trusted third party, to simply just collect all of these data sets. And once they have all the data, they can compute this function and reveal the output, right? So in this case, we still have privacy because each data holder is not saying anything about other people's data. But of course, if XYZ, if these data are privacy sensitive, then it's going to be hard to find this trusted party. So we need to consider an alternative setup where we allow these parties to communicate with each other. So they're going to, together, compute something by talking to each other. And we're going to set this up so that somehow, through this communication, they will compute a function over the combined data without seeing each other's input. So you can think of this as a secure way of achieving this ideal functionality. And this idea is called secure multi-party computation in cryptography literature. And this is going to be the topic of the second part of this talk. So I want to tie this back to what John just described. So the way I look at John's technique is that it's a clever way of doing local aggregation for distributed data sets. So what I mean by that is now we're rewriting this function f as a two-step procedure, where in the first step, each party is going to apply some pre-processing function to their data to compress their data. And once we have all these compressed data, then now we can compute the overall function that we actually wanted as a function of these intermediate results. So if we had a way of doing this, which Jon demonstrated for GWAS, then this is already very useful, right? Because now each party doesn't need to share their entire data set with each other. They can just share this compressed representation. So there's this increased notion of privacy, right? We're leaking less information. And in addition, we're having these parties compute this overall function by communicating fewer number of numbers, right? Fewer amount of data. So it's more efficient this way. But this doesn't solve everything, right? So the first issue is that this type of technique would only apply to functions that can be written in this way, where it is sufficient to look at a small set of numbers from each data set, or summary, a small summary from each data set. And OK, so f is limited. And in addition, there's no theoretical privacy guarantees. Right, so if this compressed data is just simply inner product between two vectors, large vectors, then OK, you can say that, oh, that doesn't reveal so much. But if this is something like QR factorization and you share the R matrix, like what Jon described, then is that OK to do? It's not clear, right? So there's no, so this doesn't achieve full security in that sense. So this is where secure MPC comes in. So this is a technique that can be applied for any type of function f. And for f, where you can you have this type of clever trick, then it is actually, so this can be an additional layer on top of this framework where you can perform the second step of this pipeline in secure MPC framework. Then you can turn an efficient algorithm like this one into a fully secure method. All right, so I'm going to spend the next 10 minutes or so to take a quick detour into cryptography to tell you more about secure MPC. So at the core of this framework is this idea called secret sharing. And the idea here is we want to be able to have multiple parties collectively represent some private information without giving each party direct access to raw data. So let's say we have a secret number x. And for our purposes, this will be an element in a finite field. If you're not familiar with this, that's fine. You can think of this as a set of integers modulo some prime number q. So given this private number, we can split this into multiple numbers and individually distribute them to different parties. So let's say there are n parties. And each share, I'm going to denote it using this notation, bracket x, and sub 1, sub 2, up to n. And I'm going to refer to this entire vector of secret shares using this notation, bracket x. All right. So the key property of secret sharing is that for given each share independently, this one is statistically independent from the underlying input x. So this gives you a notion of privacy, right? So each party, based on just their own copy of the data, they don't learn anything about x. And now you can make this statement a little bit stronger by saying that if you take any subset of indices, and take all, so take a subset of indices of size less than or equal to t for some threshold t. If you take all the shares corresponding to that subset, then this will be jointly independent from the underlying number x. So this is how we formalize the notion of privacy in this setting. Now, at the same time, we also want these shares to be useful in that we want them to encode some information about the private data. So how do we formalize that? So what we can say here is for any subset of size this time greater than t, so if you have access to enough of these shares, then you should be able to reconstruct x. So there exists a function that takes a subset of these shares and outputs the private number x. And this is the notion of utility. OK, So there are different ways of setting up this secret sharing framework. So let me give you an example. The simplest case is what's known as additive secret sharing. And here, what we're going to do is we're going to set each share to be a uniformly random number from the finite field. So random sample from field. And we're going to do this for all of the shares except for one. Oh, I should note that this secret sharing framework is considering their case where t, the threshold over there, is equal to n minus 1, which is which offers the strongest notion of privacy. So even if you have all of the shares except for one, you still don't know any information about x. All right, so this is how we set the first n minus 1 shares. The last share will be set to the secret number x minus the summation of the other shares. All right, so let's check both of these properties now. So let's think about privacy. So if you have a subset of these shares, it should be clear that the first n minus 1 of them is just independent random numbers, so that reveals nothing about the input. If you happen to have access to the last share, well, as long as you're missing one of the previous ones, the random number that corresponds to the missing share will hide information about the rest of this expression. So overall, given any subset that's smaller than n, it will just look like independent random numbers. Now, for utility, if you have access to all these shares, then what you can do is you can just add them all up. Then the summation of all these random numbers will cancel out this component, and you get x back, right? So in other words, the reconstruction function will just be the summation of all shares. And that's why this is called additive secret sharing. All right, so now you have a way of representing private information across multiple parties without giving anyone direct access to raw data. So why is this useful? So this allows us to perform a computation over the private data while keeping everything in the form of secret shares. So this is the notion referred to as secure MPC based on secret sharing. So let's say that we have secret sharing of two private numbers, x and y. And we want to be able to work with these secret shares to compute some function over the private input without leaking these private numbers. And the reason why I put this output also as secret shares is fairly important because it gives us composability. So if you had a way of doing this computation for this function f, and let's say we had that for another function g, so now what we can do is we can take the output from one protocol and plug this into the input of another one, right? So now what you get is the composition of these functions over the private input. So this effectively reduces this problem of MPC into defining a small set of protocols, which we call building block protocols, that do atomic operations, simple ones like addition and multiplication, division. And once you have these tools, then you can start to put these together to form increasingly complex, more useful computation. So let me give you some examples of these building block protocols. Let's say that for the input, we have two secret numbers, x and y, and they are secret shared with the parties. So what would we do if we wanted to compute the sum of these two private numbers? So this is actually fairly simple to do. So what you do is you just have each party compute the addition of their respective shares. And this will be the valid secret sharing of the sum x plus y. Why do we have privacy? Well, each party, they're not talking to each other in this case, they're only working with their local random copies of the data, so nothing is leaked. And why is this accurate? If you add up all these shares, since we're working with the additive secret sharing setup, if you add up everything, then all the x's will add up to x, all the y's add up to y. So overall, we get x plus y, so this is accurate. Now, it's also easy to think about adding a public constant to a private number. So if this is public, so this one I'm gonna, using the vector notation, we can just write this as bracket x plus bracket y. All right, so if you want to add a public constant to a secret number, this is also simple. We just have one of the parties add this constant to their share. And everyone just keeps the same share, right? So this will also add up to x plus c. Multiplying with a public constant, also simple. Everyone just multiplies their share with this public constant. OK, so given these three simple tools, now we can already say something useful. We can compute any affine function over a private input in a secure way by composing these things together. OK, now, more interestingly, let's think about the product of two secret numbers, x, y. Right, so if the first thing to observe is that if you just have each party compute the product of their individual shares, it's not going to work, because x times y is sum of all the shares of x times the sum of all the shares of y. So if you expand that expression, you get like a whole matrix, right? And if you only have local products, that will cover the diagonal entries of that matrix, but you lose all the cross terms, right? So that doesn't work. So what we end up having to do is introduce an additional ingredient. Let me write it here. Right, so the first thing that needs to happen is generate what we call Beaver Triples. So it's named after cryptographer Don Beaver. So Beaver triple is a set of three numbers, uniformly random numbers, A and B, and their product, A times B. And these will be secret shared with the parties so that they don't actually know the values of A and B. Okay, so and you might ask, oh, how do we generate these three numbers? The simplest, so there are different ways of doing that, but the simplest case would be to introduce a third party, a trusted dealer who samples a bunch of these random numbers, computes the product, and then shares them with the other parties. And note that this party doesn't need to see anything about the input. They are only working with random numbers. So let's say that we have these three things. And then what the parties can do is they can reveal blinded input. So let me explain what I mean by that. So they're going to compute x minus a, y minus b, using the tools that I talked about here. And then they'll simply just combine all these shares to reveal the values of x minus a and y minus b, and these will now be considered public numbers. And why is this okay to do? Well, these parties don't know the values of a and b, so and they're random numbers, so they completely hide information about x and y. Now, the last step is where the magic happens. So now we can rewrite x times y as something like this. Okay, and then if you expand it, you will see something interesting. Okay, so we started out with the product of two sacred numbers, but now we have an expression where these things are public numbers. This is public, public. So this is now an affine function over sacred input. And we already established that we can compute any affine function over private numbers, right? So now we know how to compute this. So in particular, the secret sharing of the product x times y will be something like this. So just one party adds this term. This will be the sacred shares, and like that. So it's an affine function. All right, so that's how you do multiplication. And if you combine that with this part, then now we have a tool that can compute any arithmetic function over the private data. And now you can think about how to use these techniques to build interesting, more useful linear algebraic operations like PCA, right? So I hope you are getting the big picture here. So let me go back to the GWAS setting for the last 5 minutes or so. So when you take this MPC framework and try to apply it to a real problem, oftentimes you run into scalability issues. Because note, like, all the work that we have to do for one pairwise multiplication, right? So if you have a computation that has many pairwise multiplication, it's going to be very expensive. And especially the key step in GWAS that is most challenging in terms of doing it in MPC framework is this step called population stratification correction. So there, let me write it down. So here, the idea is that if you run GWAS, you might find spurious associations that are tagging for ancestry structure in the study cohort, not the meaningful biological patterns that we hope to capture. So a common way to tackle this bias is to run something like PCA to get the top components from the genotype matrix and use that as a proxy for ancestry structure, and then include that as a covariate in your GWAS computation. So the question is, if we want to do something like GWAS over distributed data in a privacy-preserving way, then we also need to be able to do something like PCA on the distributed data as well. So the question is, if you had the sacred shares of distributed genotype matrix, can you use MPC to compute the PCA of this matrix? So this will be a key problem. Now, what is PCA? Just to give you some intuition, this is going to be our genotype matrix with individuals on one side and genomic positions on the other. And PCA is equivalent to performing a truncated SVD. Which is a form of low-rank matrix factorization. So we're representing this matrix as a product of 3 matrices that look like this. And we'll pick the top k components or something like that. Now, so these, the right singular vectors, these will be the principal components that capture dimensions in the genotype space that capture most of the variation across individuals, and that will typically correspond to ancestry patterns. And these row vectors in the left singular vector matrix is going to be the covariate, right? So this gives you the weighting terms on each of the PCs for each individual, and we're going to include these numbers as covariates for the corresponding individual. So this is how PCA-based population correction works. So if you wanted to do PCA, we need to be able to solve this factorization, right? And doing that in MPC is difficult because this requires an iterative algorithm that involves repeated multiplications over this large genotype matrix. And this could be very large, right? If you have a cohort of, say, 1 million individuals, this could be on the order of 1 million by 1 million. And so running any type of iterative algorithm is going to be very difficult because you need to generate a lot of those Beaver triples that I mentioned. So we need extra tricks to make this work in practice. So let me give you just brief ideas. So all this is going to be, you can find more details about these tricks in my recent publication from last year, which you can look up. All right, so let me just give you a brief overview of the techniques here. So the first technique is that observe that we're only interested in the top few components of this matrix, right? So instead of working with this entire matrix, we can actually think about compressing this, this dimension and working with the reduced matrix instead. And that will capture most of the top PCs accurately. So that's this notion of random projection from randomized numerical linear algebra literature. So basically, if we have x, we want PCA of x. But instead of doing that, we're going to hit x with what we call a sketch matrix to reduce this dimension. So x looks like this. Omega is a tall and skinny matrix. And then solve the PCA problem there. And that will be an approximation of the original problem. So that way we can reduce the scale of the problem without affecting the accuracy too much. Now, oh, sorry, yeah. Okay. Okay, so this is what I wrote over there. All right, so in practice, to get an accurate approximation, doing just this is not enough. What you end up having to do is use what's called a power iteration algorithm to improve the accuracy. So we actually still have this problem of having to multiply the original input genotype matrix multiple times, which is very expensive. Right, so it's going to look something like that. All right, so this is where we need our second technique, which is to reuse Beaver triples. So here the idea is, before I describe to you how for each pairwise multiplication, we need to generate these random numbers to be able to do multiplication. But if you use the same input number multiple times, then it actually turns out that you can use the same random number that corresponds to that input over and over again. So that's actually very important in this setting, because now what we're saying is that we can just generate one random matrix for this large input genotype matrix and use that throughout this entire process. So that reduces the complexity by a lot. And now we still have this problem of having to ship around this random matrix, very large random matrix, between the parties. So we can actually further make that more efficient by using what we call shared pseudorandom number generators, PRGs. And here the idea is, because we're sending random numbers around, instead of having the parties sample them and then transfer them over the network, we can just have them have synchronized PRGs for all these parties, and they can independently sample from the same random stream. So this is a way of compressing communication, and this works only because we're working with random numbers here. So by combining these three techniques, we were able to build this end-to-end secure GWAS framework using MPC tools, and the results of that is described in this paper. And there we can achieve accurate GWAS results within a reasonable runtime. So for a GWAS data set with, say, 1 million individuals, our runtime turns out to be around a couple of weeks. Actually, in the paper, we say a couple months, but recently we were able to get it down to 2 weeks. So if you're interested in that, I would be happy to talk to you. Thank you for listening.
Thank you, John. Thanks. May I begin with a slide that's not linear algebra, but it's about deep learning? I just thought you might be interested in a quick report on progress on what's been a very fundamental problem with deep learning. You know, the deep learning uses many weights, parameters, to fit the training data. And the usual rule is that if you use too many weights, you overfit the data, and your error goes up when you apply it to new data. That's the usual expected thing, but it didn't happen. Deep learning succeeded. We were, by taking many parameters, fitting the data often now exactly. Overfitting didn't wipe out the value of the work, and this picture has become, this double descent picture is showing up on a number of papers that aim to explain it. This is not my work at all, so this is just a report. So this would be the usual picture of the, so the training error goes down as you do more, as you have more parameters, at least squares, say, but the error in fitting new data, unseen data, has a sort of good point, but then goes up again. That's the sort of standard picture in statistics. And the novelty is that after exact interpolation, it comes back down. So that's, and right now there's not, the explanations are quite significant, quite deep, quite a lot of analysis there, but I thought you might like to know that picture. Okay, onwards to linear algebra. Oh, this is related, that but with too few data, you can fit it, but the error is all over the place, as we know from ordinary interpolation. But now with 4,000 points, the overfitting doesn't, the overfitting begins to disappear and you get a good fit. Good, okay, that's just sort of information for what's happening in deep learning theory. Okay, some matrices. This is the right way to start linear algebra. So they're kind of, do you see anything special about that first matrix? So it's 3 by 3, and maybe if you look at it a while, you'll see that the columns are all multiples of the same column, right? 1, 4, 2, if I multiply by 3, I get 3, 12, 6. If I multiply by 2, I get 2, 8, 4. So that's a matrix of rank 1, only one independent column. And that's the building block, as actually appeared already this morning, of more general matrices. And notice that the rows are also multiples of the same row. That's automatic. If the column space has dimension 1, rank 1 matrix, then also all the rows are multiples of 1, 3, 2. So that's just an example of a very simple matrix. Here's the second one, A1, is obviously not rank 1 because I see that row 1 and row 2 are different. So we've got at least rank 2. What's the rank for that matrix? You have to help. So how many independent rows have we got? Only 2, because the third row is the sum of the first 2 rows. So that's a matrix of rank 2, and linear algebra says that there are only 2 independent columns. I don't see, and it would take a little more time than we have to find some combination of the 3 columns. Must be 0. Must give the 0 vector. If there are 2 independent rows, then there are 2 independent columns. Okay, we'll see a little more about that. That's the first and main theorem in linear algebra. Here are some symmetric matrices that I like. This -1, 2, -1 pattern, second differences appears all over applications. Here's a matrix of a different sort. The columns are cos theta, sine theta, and minus sine theta, cos theta. What kind of a matrix is that? That's a rotation. So that would be an example of an orthogonal matrix. The dot product between that column and that column is 0. And the lengths of the columns have been normalized to sine squared plus cos squared to 1. So these are the symmetric matrices like that are sort of the kings of linear algebra. And orthogonal matrices are the queens. And here's a sort of random matrix that we'll see. Okay, whatever. I don't know how he got in there. Yes, okay. So can I just start at what I do in the very first day of linear algebra? So here's a slightly different matrix, but a key point about matrix multiplication, multiplying a matrix by a vector. So that's what I'm doing there. A matrix times a vector. And what is that right-hand side showing? It's showing that the result is a combination of the columns. A times x gives a combination of the columns. That you really want to see these multiplications a column at a time, vector-wise, and not if you just did row 1, 1, 4, 5 against x1, x2, x3, you would certainly get x1 plus 4x2 plus 5x3, but you'd miss the point. The point is that do it by vectors, that we get a combination of the columns. Okay, so let's take that one more step. Suppose I take all vectors AX. So I have the matrix A. I'm looking at a fixed matrix A, and I multiply it by all possible vectors X. So I get all linear combinations of the columns. And I'm wondering, what is that? In this specific example, we can understand we're in 3D. So, for example, do I get all vectors in 3 dimensions? Do I get the whole space, 3-dimensional space? Or when I take, so everybody knows what I'm doing, I'm taking all combinations of those columns. Any x1, any x2, any x3, take that combination, put them all together, you got a whole lot of points. It's being linear algebra, that collection of points could be the whole space. That would be for an invertible matrix. It could be just a plane, because we're in linear algebra, it would be a plane. We won't get a curved surface out of taking all combinations. And what's the answer here? A plane, thanks. It's a plane. Because the first 2 vectors are independent. They're the first 2 columns, 1, 3, 2, and 4, 2, 1. Those point off in some directions. But 5, 5, 3 is the sum of the first 2. So it's on the same plane as the first 2. The third vector did not get us off the plane. And we have a 2-dimensional, we have a matrix that's singular, it's not invertible, its column space is only a subspace, a plane. Right. So that's a typical example to start with. Okay. The answer is plane. Okay. Now can I bring out the word basis, because that's what you need to compute. So a basis is columns that are independent. We said that our matrix, I'm thinking about the same matrix here, we're thinking about there were only 2 independent columns. Those 2 vectors will be the basis for the column space. And 5, 5, 3 doesn't go into the basis because we already have it. So this leads us to the first neat factorization of a matrix. So that's what I want that will be the thread on which this hour is organized. Matrix factorizations. So here's one. A matrix factorization of my matrix A. You remember my 3 by 3 matrix A. So it had these 2 columns. So those I want those. Those are the column bases. So those are in the matrix C. And here's the matrix R that takes the right combinations. Do you remember the first column of A was 1, 3, 2. So I want 1 of that column and 0 of that column in column 1. What was column 2 of my matrix? It was 4, 2, 1. So out of this factorization, I want to take 4, 2, 1 times nothing of that plus 1 of that. That's the 4, 2, 1. All good. First 2 columns we're just creating. The point was that the third column is 1 of that column plus 1 of that column. So we didn't include that third column in C. So do you see what we have here? We have a matrix of rank 2, and we've factored it into a 3 by 2 matrix. We only needed 2 columns in the basis, times a 2 by 3 matrix, or sort of the row basis or something. And actually, this leads to a nice proof of the fact that if two columns give a basis for the column space, then two rows will give a basis for the row space. So the two spaces, the column space and the row space, have the same dimension. That's a remarkable fact. You know, if you had a very large matrix and wondered how many independent columns it had and how many independent rows it had, it wouldn't be clear that that number is the same, but it is. Okay, so that's a big fact about in linear algebra. Okay, and then we're often solving equations like ax equals 0. X is always a vector here. Ax and 0 is a vector, so this is a set of equations with zeros on the right-hand side. And if it's natural to want to know how many solutions does it have. Well, so the rule is just what you would expect, that if x has n components, then we might have n solutions. But if they have to solve this equation. If A has rank R, then this is the count here. The counting theorem is that AX equals 0, how many solutions does it have? And when I say how many, I mean how many independent solutions. There will be n minus R. R equations are really there. You have n variables, so n minus R is the count. So these first slides are just getting these basic facts about basis, counting, dimension, rank, and now I'll go to the, I can say more about these spaces. Yeah, this is like, I'm kind of happy about can I show you the picture here? For me, that's the big picture of linear algebra. Everybody who takes 1806 must. Have you taken 1806? Probably not. But anyway, you cannot get through that course without getting this picture straight. So over here we have columns. Over here we have rows. Oh, vice versa, I didn't read. Columns are over here. Rows are over here. Okay. So what is the row space of the matrix? The row space of a matrix is all combinations of the rows. It was a plane in the 3 by 3 that we had. And then the null space is all solutions to AX equals 0. And the point is that these two spaces they combine to give the full n-dimensional space. This has dimension R. This has dimension n minus R. And that's the result of looking at rows. Over here is the result of looking at columns. So we looked at the columns of that 3 by 3 matrix. There were only 2 independent columns, so that was a plane. And then the null space of A transpose would be one-dimensional because I want to get altogether 3. So 2 and 1 there, 2 and 1 here. You see, just the idea is to see what's going on, what a matrix is really doing. What is a matrix really doing? It's every vector in this null space is headed to 0. That's what the null space means. A times x is 0. Every vector in the row space is headed for the column space. Those have the same dimension, R. So what a matrix really does is take this R-dimensional row space, multiply by A, you get something in the R-dimensional column space. And then these null spaces just sort of disappear. When you multiply by A, that takes the vector to 0. So I hope you admire this picture. It's just like, okay, those are the 4 spaces so a space is like a plane, like a line, like the whole space. And there you see these two spaces of equal dimension. So A could be any size, 5 by 10. Its rank might be 4. Rank meaning 4 independent vectors in the column space, 4 independent rows in the row space. So this would be size 4, that would be size 4. Then the null space would be, and the null space of A transpose would complete the picture. Okay, so that's, there we've really sort of, that's the first half of the course. Gosh. Okay, now, ready for the second half. So that's the serious linear algebra now. Factoring the matrix A. So all the different things you did. So this morning we already saw the QR. QR got mentioned. That was a factorization of a matrix A into Q, which is an orthogonal matrix, and R, which is triangular. Well, I'll come to that one. There are 6 big ones. 6 big factorizations. But first, allow me to multiply 2 matrices. You will say, I know how to multiply 2 matrices. But do you know this way? This is really a higher level way. That when I multiply 2 matrices, I can look at the columns of the first. The usual way is row times column, giving a dot product, giving a part of the answer. Here we're looking at columns times rows. Columns times rows. So say the first part of the answer. So a column times a row is a full-size matrix. Column B1 multiplying row C1 star. There we are. Now, if I just look at that part of the answer, what are you seeing in this part of the answer? If I have a column times a row, what's the rank? What is the rank of a column times a row? It's rank 1. Those are the building blocks. Because every column, this is a matrix, right? M by 1 times 1 by n is going to be m by n. It's going to be a full-size matrix. And I'll have n of those to get the whole result. But if I just look at one of them, that is a rank 1 piece, because every column of this matrix is a multiple of B1. Every row is a multiple of C1 star. This is a rank 1 matrix. This is linear algebra, really. To understand the whole matrix, we'll find all these different choices of B and C, and the result is different ways to break up a matrix. Some of those are ways you know. Do you know? I'll describe some of these. Do you know what these refer to? So LU, do you know what LU refers to? If in MATLAB, for example, if you do LU of the matrix A, what do you get? What are L and U there? That comes into elimination. Gauss in solving AX equal B. That will come first. QR got mentioned this morning. These ones are about eigenvalues. This one is about singular values. That's the SVD, the singular value decomposition. So that's sort of the high point of this whole talk. Okay, right. So can I start on this list? Everybody knows I have a matrix A. It's, in principle, can be rectangular. And I want to see what those mean. Okay. Oh, first I have to say, the Q showed up there. So and we had an example of an orthogonal matrix. You remember cos theta, sine theta, minus sine theta, cos theta, that rotation? Well, in n dimensions, we have a matrix Q. So the point about a rotation is that if I just transpose it, that rotates it back, so that's the inverse. The transpose is the inverse. Q transpose, for a rotation, for an orthogonal matrix, Q transpose times Q is the identity matrix. So inverting the matrix, that's why QR gets into every talk about linear algebra, because inverting Q, you only transpose it. Do you see why it's, so the columns are all orthogonal. So Q1 transpose Q1 gives me the 1. I normalized to length 1. And Q1 transpose times the other columns is all zeros. And that's true for every row. So Q transpose times Q is the identity. That's the definition of an orthogonal matrix. And I'm thinking of these as square. So also Q transpose is the identity. Here's the same thing with the column times row multiplication. So orthogonal matrix, just think rotation. And what's the point of picking out orthogonal matrices as being so good? If I multiply orthogonal matrices, I'm just rotating again, rotating, maybe reflecting. It's still an orthogonal matrix. I can multiply orthogonal matrices forever without exploding, without having numbers that overflow, without having numbers that underflow. Products of orthogonal matrices are just like, it's just like multiplying 1 and minus 1 forever. You don't get big, you don't get small. So there, the goal in numerical linear algebra is to work with orthogonal matrices. For example, in deep learning. So every layer in deep learning, a big issue is if you have a deep neural net, 10 or 20 or 100 layers, if those are orthogonal layers, your numbers stay where they should, stay in a reasonable range. If you don't have orthogonal matrices, then the numbers after 10 or 20 layers have blown up or died away. So really orthogonal is the goal. Okay, all right, okay, so I'm now thinking about these. This is the rest of the talk is really to tell you about those factorizations, because they express linear algebra. And the first factorization is LU. And there it is. So there's a 2 by 2 matrix. Oh, I'm thinking at the top there is 2 equations. How would you solve those equations? Well, that we know. How do I solve 2 equations? I subtract 2 of the first equation from the second, and I get, and then x is eliminated. So this is Gaussian elimination. Subtract multiples of equations from equations below until you get to a triangular matrix. Of course, here we got to that triangular matrix right away. There were only 2. We did 1 subtraction. We took 2 times. So the multiplier was 2. There's the multiplier. And I just want to see this as an example of, so the first lines show elimination, what everybody learned to do in high school. Subtract a multiple of the first equation from the second, so you get a triangular system, and then it's easy to solve. The second line is the same thing, but undergraduate, 1806 level. You're writing what you did up there was to factor the matrix into lower triangular times upper. I'm just really showing you an example here. So can I say it again and just put it in a sentence? The usual Gaussian elimination process, which the Chinese found 3,000 years earlier, is factoring a matrix. What it's doing is it's producing an upper triangular matrix And the link between the original and the final is a lower triangular matrix. So A equal LU, that's just fundamental. But it's actually a little tricky to let's see. Here we go. Could I explain that L times U? It's not so simple to see that if I start with a big matrix A, big square matrix, and do this elimination stuff systematically, which is what MATLAB will do. Every linear algebra software does elimination. That the result is lower triangular times upper triangular. So the natural steps of elimination amount to factoring the matrix into L times U. It's the right way to see what you've done. So this middle part shows what you did. Now, can you see can I talk you through that elimination? So what did elimination do? You took row 1 of the matrix. That's the one you're going to use. That's the pivot row. That's the row you're going to use to clean up the first column. So you took row 1 of the matrix as it is with that 1 up there. So row 1 you just reproduced. But then you multiply row 1 by these, which is multiplying the first equation by these suitable numbers, so as to get zeros so as to match what's in the matrix. So you've chosen those L's to match the first column, so that what's left is zeros. What I'm trying to say is that equation expresses elimination, expresses the idea of elimination, is that I'm removing multiples of row 1. I'm removing the right multiples of row 1 to get that. That's what elimination did. The first multiple was 1. I'm removing the whole row. The other multiples were whatever it took to get the first 0. Do you see that? So here I'm saying that elimination starts with A, factors out this rank 1 piece. Can you spot rank 1 matrices now? Column times row. Eliminates this rank 1 piece and leaves with a problem that's one size smaller. And then you just do it again and again. So you repeat that step. You take the pivot row is now the row of A2. You subtract the suitable multiples of that so that you get zeros. And then if you put it all together, this is what you've done. You've taken that times row 1 of the matrix, that's there. Then you've taken this times that row of that matrix, which shrunk it by 1 more. You take that times the next row, shrunk it by 1 more. The last one looks like that. That's LU. I'm talking too quickly, actually. But do you sort of see I'm claiming this is the matrix way to think about elimination. Elimination, you're just doing what you would naturally do. Just like you get up in the morning, you get somebody come to work, somebody gives you a 5 by 5 system of equations. What do? Just, and now, of course, linear algebra is saying, what were you really doing? That's the math part. What were you really doing? And what you were really doing was subtracting multiples of the rows, the pivot rows, and these are all the multipliers, so that you're breaking the matrix down to piece, and when you put those pieces together, you see the lower triangular L, all the multipliers were here. You see the upper triangular U, all the pivot rows were up in the upper triangular part, that's LU. So, you know, a person can live a happy life without knowing about LU, but it's the first basic factorization of a matrix. Okay, let me go on to the second. Remembering what orthogonal matrices are. Yeah, these are facts about orthogonal matrices, which are so valuable. So now this factorization is usually associated with Graham and Schmidt. Graham and Schmidt, what did they do? Or what did Graham do? I don't know what Schmidt did because there's nothing left to do after Graham. So you've got a bunch of vectors, independent. Let's say they're independent, but not orthogonal. You want to orthogonalize them because you want to get to a matrix Q with orthogonal columns. That's what you can compute with. That's what you can invert easily by just transposing. So Graham-Schmidt was a systematic way of starting with these A's, these columns, producing these Q's, these orthonormal columns, perpendicular to each other, and then some coefficients, as always, connect the Q's back to the A's, or the inverse would connect the A's to the Q's. There's a connection matrix R, and it happens to be triangular because Graham-Schmidt is done in a certain order. You take the first column, then you take the second column, make it orthogonal to the first, then you move on to the third. And that order, that sequence, makes R triangular. I could do the next slide would take with more patience that step, but QR is really basic. It's often the first step with a very large matrix. It's not expensive, and it gives you a basis of Q's, an orthogonal basis that the remaining computations are reliable. So that's twice as expensive as elimination, but elimination and QR, orthogonalization, Graham-Schmidt, those are operations on matrices that, in principle, you could get exactly right in a finite number of time, Okay. So now I'm moving from those two basic ones to which are just using subtractions and maybe square roots. I'm moving from those QR to the big factorizations, the not at all obvious factorizations of diagonalizing a matrix, so eigenvalues, eigenvectors, singular values, singular vectors, principal components, all that's coming now. And that'll be the end. So this is the first half. And now for the next half, those finding eigenvalues or singular values, you cannot do in a finite number of steps. It's equivalent to finding the roots of some high degree polynomial. You can't do that. Abel showed that beyond fifth degree, you can't do it. So these next factorizations are of a different kind, but actually, numerical analysis knows how to do them approximately quite fast, as long as the matrices are not too big. So this is the A equal QR comes directly into least squares as it did in the morning lecture. Let me just, and projections, I'm skipping some nice geometry here that least squares amounts to projecting your vector B, your right-hand side. Least squares is for equations that you can't solve exactly. You can't solve AX equal B. You've got too many equations, too much data. So to get something solvable, you project down into the column space. You throw away part of B, the data B, and you keep the part that's a combination of the columns. Then you can solve. Yeah, so projection is a beautiful picture of a key step in linear algebra. The geometry of linear algebra really is part of what to know. Okay. Now, ready for eigenvalues and eigenvectors. Then we're there. Okay, so what's with eigenvalues and eigenvectors? The matrix I'm calling S for symmetric. And the point is, why am I doing eigenvalues and eigenvectors for symmetric matrices? The point is that the eigenvalues are wonderful and the eigenvectors are wonderful when the matrix is symmetric. That's why those are the kings of linear algebra. What do we know about the eigenvectors of a symmetric matrix? The eigenvectors of a symmetric matrix. Those are orthogonal. The eigenvectors are orthogonal. The eigenvalues are real. That's good. The eigenvectors are orthogonal. That's phenomenal. That is really important to get orthogonal vectors. So that's a straightforward fact. I've seen it on so many PhD exams. Yeah, it's worth learning why, but I probably don't take that step this morning to show that the eigenvectors of symmetric matrices are orthogonal. Everybody here understands orthogonal things, orthogonal polynomials that's the same idea. The orthogonal polynomials, and Fourier series. Why does Fourier series work? Because the sines and cosines are orthogonal. Yeah. Why do Legendre polynomials work? Because those polynomials are orthogonal. Really, orthogonality is it helps you to visualize and it helps you to compute. Okay. So here we have eigenvalues and eigenvectors. So line 1, S is our matrix. What are the Q's? Those are the eigenvectors, and I'm using Q because they're orthogonal. So S times Q is, the whole point of eigenvalues is lambda times Q. And then from that second line, lambda 1, Q1, going along, I split it apart with the Q times the diagonal matrix. Actually, that first line, which is repeated here in matrix notation, is the key, is so important. S times the eigenvector matrix gives lambdas times Q's, and then I can pull out the lambdas, they show up on the right-hand side, times the Q's, and that is SQ equal Q lambda. But now, look at SQ equal Q lambda. Multiply on the right side by, what do I multiply on the right side? Multiply on, take that equation, SQ equal Q lambda. That's just saying that Q has the eigenvectors, lambda has the eigenvalues. Now, what do I multiply on the right by? Q transpose, which is the same as Q inverse. Why do I do that? Because when I multiply by Q inverse on the right, it kills that Q. So I have a formula for S. The spectral theorem of linear algebra. The spectrum is the eigenvalues. The spectral theorem says every symmetric matrix factors into orthogonal times diagonal times transpose of orthogonal. That's like, I'd say that's theorem number 1 in importance. And of course, we can split that up into a sum of rank 1s. So that's the picture when the matrix is symmetric. Square, of course, and symmetric. And now, what's left? All the other matrices. Not square, not symmetric, What can we do with those? They don't, if they're not square, they don't have eigenvalues. AX equal lambda x doesn't make any sense. What do you do for all the other matrices? And most linear algebra courses end here. But now you really have, because of what's happened in the last generation, you have to know the next step. What do you do for any matrix A? Okay, so here we go. So this is the climax, you could say, of the course. Okay, so this is all symmetric. Now, okay, if we have not symmetric, then we push ahead. But let me go to what are we going to do when A is maybe not square, not symmetric, eigenvalues don't make sense? Where do you get to a good matrix out of an arbitrary matrix of data? Think of A as just a matrix of data coming from genetic experiments. So it's a big rectangular matrix. The good matrix is A transpose times A. The good matrix is A transpose times A. Why is that good? Or A times A transpose. That's a different. So I have two, that's the point here. If I start with a matrix A not square, or a general matrix A, I have two different good matrices, A transpose and A transpose A. So why are those matrices good? What do you know about A transpose times A? Why am I wanting to get to that matrix? Because it is symmetric. It's symmetric. And more than that, it doesn't have any negative eigenvalues. It's a terrific matrix, except for the fact that I don't want to compute it. Sorry, I have to be truthful here. So if A is a big matrix, multiplying A transpose times A is like, don't do it. You want to do it in theory, but you don't want to do it in reality. So for now, it's theory here. So what's up? The point is these have the same eigenvalues. That's can prove in a line. But they don't have the same eigenvectors. They're different matrices. They're probably different sizes. So they've got different eigenvectors. So the result is here, for this rectangular matrix A, there are two sets of eigenvectors. There are the eigenvectors that way, and then there are the eigenvectors that way. Those are both, they're different, and those are called singular vectors. So any matrix A has two sets of singular vectors. The eigenvectors of A transpose A, which are orthogonal, of course, because the matrix is symmetric, and the eigenvectors of A transpose, also orthogonal, but different. And then from that comes the singular value. Oh, okay, so here's the climax. Let's look at the matrix line and then the geometry, and then we're done. So what do I have here on the matrix line? There's the SVD, the singular value decomposition. What do you see there? You see two sets of eigenvectors, U and V, not one anymore. And you see the orthogonality, right? U transpose U is I and V transpose V is I. But they're different. And in between comes the diagonal matrix as usual, but the sigma matrix is singular values, different numbers. Well, we don't even have eigenvalues for these matrices. Okay, so that's what the singular value decomposition says. You just write it out. But then you might like to draw a picture. So first, to know how many singular values there are, there are the rank, that number that we started with at the beginning of the hour, the number of independent columns, the rank, tells me like how many, what dimension, what's the real dimension of my matrix. So that counts the number of positive singular values. And then this is an attempt to draw what the SVD is telling us. So the SVD is telling us that every matrix A factors into orthogonal times diagonal times a different orthogonal. And if I try to say that geometrically, every matrix A is the product of 3 steps. First, a rotation, that's the orthogonal guy. Then a stretch, a diagonal matrix. Then another orthogonal matrix and probably different one. So if I had a 2x2 matrix, for example, there would be a 1 rotation angle. There would be 2 stretch distances, two singular values. There would be another rotation angle, 1 plus 2 plus 1. That would account for 4, the number of the 2x2 matrix has. So that's the SVD. That's the right way to look at a matrix, because what do you do now? You take the large singular values with their singular vectors, and you throw away the little ones if you've got data. So that's the key point. That's PCA, principal component analysis. The principal components are the eigenvectors, the singular vectors, and PCA would keep the big one and throw away the little one. So it would have a low rank approximation, rank 1. Okay, maybe there's something on a final slide here, as often is. Oh, well, how to prove the SVD I won't do here, and there's an example of the SVD. Yes, here's the good point. So the SVD, the singular value decomposition, breaks a matrix up in a new way, a new factorization of so line 1 there, singular value sigma times left singular vectors times right singular vectors. And they're different because A is not symmetric. And then the question is low rank. How do we use the SVD? How does PCA work? PCA says most of the variance is in the first biggest singular values. So that second line with about AK is just keeping the top K singular values, right? And then the great fact is that that's the best matrix. That AK, where you've just kept the K top pieces, the K biggest pieces, the K greatest variances, that's closer to your original A than any other could be. So it's the right way to do dimension reduction. But shall we allow 1 minute to the actual computation? So if you call MATLAB or any code for the SVD, it will compute it if your matrix is order 100 or 1,000. That's pretty amazing. But I'm remembering very well the day that Nick Patterson came to say, I have a genetics matrices of size 10 to the 4th or 10 to the 5th. What do I do for their SVD? And I didn't know. I had no answer what to do for the SVD of a giant matrix of Broad Institute size, right? So what do? Randomized linear algebra has been created to solve that problem. So that would be my final. So randomized numerical linear algebra for very large matrices, you can handle them by sampling the matrix and not working with the full matrix. So that's what Nick Patterson did, and satisfactory. Okay, so I won't say more. I won't say more of anything. Just thank you for patience for allowing me to put so much linear algebra into an hour. Thanks. Yeah. Thank you. Okay. And this is just a reference to the linear algebra, the 1806 text, and this is, maybe do you know that I got into the deep learning part? So there's a new course and a new textbook for 1806-5, and these are the websites. That's really what I want to show. At math.mit.edu, linear algebra is for 1806, and learning from data is for 1806-5. So those are two courses now in the math department, but you know that linear algebra is everywhere. Thanks.